And welcome back to another episode of Magnetism with our host, Mr. Gala. Hello, thank you. So today we're going to talk about the magnetic force on particles and wires. And so to start off, we figured out there's these things, magnetic fields. And so there's this thing, magnetic forces, right? When we have magnets, they get attracted to each other. They sometimes repel each other. You know, stuff gets crazy sometimes. And so to kind of quantitatively figure that out, which means, get numbers in there, we have this equation that says our magnetic force is equal to Q, which remember represents the charge, multiplied by the velocity of the particle. I know velocity, rearing its ugly head again. Multiplied by the magnetic field. And so when we multiply all these things together, we get our magnetic force. Now a quick side note, magnetic fields actually have the units of Teslas. Now, I know it would be awesome to say it's the car, but it's not. It's after the guy Nikola Tesla, who did all sorts of crazy experiments with electricity and magnetism. He did some wild stuff. But anyways, with these magnetic forces, the magnetic force on a particle, or a moving charged particle, is always perpendicular to the magnetic field and the velocity of the charge. Now, we'll talk about kind of how that all is perpendicular. Basically, it's an x-axis, y-axis, z-axis kind of thing. And so we have this alternative right-hand rule. And so this leads us to our right-hand rule. Now the rule is the thumb always gets the direction of the velocity. The magnetic field, which remember is B, we'll label that really quick, magnetic field, is always represented by our fingertips, and the magnetic force is always coming out of our palm. And so, for example, if we have this particle over here, let's just say it's moving to the right. When we do this, we follow, I don't know where our hand went, there it is. We follow our rule, so our thumb goes in the direction of our magnetic field, so stick it out. We got our thumb going that way. Now the X's, does that mean in or out? You guessed it. That means it's going in. So we got our fingers going into our computer screen, our thumb going off to the left. Our palm is facing which way? Hopefully, if you use your right hand, it would be pointed down. So our magnetic force is going down. And so that's kind of the simple, easy, basic way to figure out the direction of all of these things. Now, we can use this right-hand rule as long as we have two of those three possible things. We need the magnetic field and the velocity, the force and the velocity, or the magnetic field and the magnetic force, and we can figure out the velocity. Now, one really important thing with this right-hand rule, obviously use your right hand, but if you cannot orient your hand in a fashion that actually allows for the right-hand rule to be used, meaning it's impossible for you to twist your hand in some sort of crazy fashion to get it that way, there's no magnetic force. Or if we're talking about, let's just say velocity, if you're trying to determine the velocity and it's impossible to figure it out, that means that the particle itself isn't actually moving. And so, with these magnetic forces, we just talked about how they exist on single particles. They also exist on current-carrying wires. Now, it's a slightly different equation, so our magnetic force is equal to the magnetic field multiplied by the current. So remember, B still stands for the magnetic field. And then I, hopefully you guys remember, is current. And then we multiply it by the length of the wire that's within the magnetic field. Which means that the more wire that's in the magnetic field, the stronger the force is. Which kind of makes sense, right? If you put a bunch of it in a magnetic field, it should have a bigger force than if only a little itty bitty section is. And so if we do this, and we just kind of follow this basic rule, if we follow our rule, we got our current carrying wire over here. We got our current going up. Our magnetic field, remember X's mean that it's going into the page. And so if we follow it, our thumb goes in the direction of our current, which is kind of like our first right-hand rule, right? Thumb in the direction of our particles moving that way. So our thumb goes in the direction of our current, our fingers are going into the page, and if we have this open palm, our palm should be facing off to the left, giving us this magnetic force that's going off to the left. I don't know why my pen is doing that today. And so we have these current carrying wires that essentially generate these magnetic forces. But that was it. I'm your host, Mr. Gala. Thanks again for signing in. You say sassy, Spartans.